So we saw how to work with series objects. Now let's focus more on data frames. So let's see how we can select data from within data frames. So there are different ways to do that. First, about selecting columns. The way we saw until now is to just use the square brackets and give the column name, and that will give us the whole column as a series. Now, instead of giving just a single string, which is a column name, we can give a list of strings to get a few columns together. And this will give us a new data frame with just a subset of the columns. Okay, so here we just want the family, the genus, and the subunits. And we get a new data frame, which is actually just a view of the original data frame, restricted to only these 3 columns. And notice that in the last example, we give a list of just 1 column, and we still just get, we this time get a data frame instead of a series, but with only 1 column. Okay, so notice the difference between this and this. So here we use the square brackets to access a column, and here we again use the square brackets, but within it we give it a list. So the twice square brackets here are actually important. That means we'll get a data frame and not a series. Now you can also see sometimes people access to columns as distinct attributes, like you see here. So you can access a column like an attribute, just giving the column name. So here we have the data frame dot the name of the column, and we actually get the same thing that we would get if we were just to query the column directly using the square brackets notation. So this is some kind of synthetic sugar that Pandas gives you, but it's actually recommended to avoid that because it won't support anything that cannot be referred to an attribute. So for example, if you have a column which contains spaces or any other kinds of symbols which are not valid attribute names, this won't work for you. So I actually recommend you to just stick to the square bracket notation. Now, if you want to access something by position and not by the actual keys, labels, index, whatever you call it, then instead of the lock attribute, you can use the iLock, which says you want something by position. Okay, so when we do df iLock 5, instead of getting the record that has index 5, we just get the 6th record, no matter what it is, even if we have string index. Okay, and likewise, if you use the iLock 5 to 8, we'll get everything between 5 to 8, not including when these are referred to as positions, not as the index. Okay, and you see that indeed we get the 6th, the 7th, and the 8th rows of the original data frame. Now, I should say that the terminology used in Pandas is somewhat confusing. So the word index will typically refer to the actual keys or labels or whatever you have within the series or the data frames. And when you speak about positions, you will just hear people saying positions or positional indices, which is somewhat different than the terminology people use when speaking about list, for example. So when people refer to the index of a list, they just refer to positional index. Okay, but here it's different. It has this more confusing terminology. And actually, most of the function with Pandas that we've seen and we're going to see work with the actual index, not the positions. So the index is more important for most use cases than the positions. Now, remember that if we use the lock instead of the iLock, we'll refer to things by their actual index. So lock 5 will give us whatever record we have with an index of 5, even if it's the 200th record in this case. It will still give us that record, regardless of where it's positioned. And also note that when you use the lock with the slicing syntax, then again, this is by labels. This could be strings just as well that you give here. And also note that when you do this, it will actually include the last one when you do that to a data frame. So data frame lock and then a range of indices will give you everything in between them, including the last one. Whereas the ilock will not include the last one, like it's the more convention in Python. So you can see that here we actually get 4 elements, 4 records, and not 3. It includes 8. Now you can use the lock to access both a specific index and specific column, or a range of indices and a range of columns together. So if you do data frame lock and then index and a column, you will get a single entry, which is just a value with this record index and this column. In this case, it will be 60. So you will get a subunits of virus number 5. Now, if you give a range in the index, you will get the sub, but give a specific column value, you will get a range here of 3 values as a series. So you will get the subunits of viruses 5, 6, and 7, which you see here. And likewise, if you specify a specific index but give a range of columns, you will again get a series, but this time the index will be the column. So you'll get all the columns between subunits to outside SESA. However, they are ordered in this case. So it will just refer to the ordering and give you everything in between these 2 columns, including the last one. So you can see that indeed gives you all of the columns and their corresponding values as a series again. And like with NumPy, you can use the column just to specify everything. So that's actually a different way just to access a specific row. So for row with index 5, you'll get all values, which again is a series. And if there are multiple values for both the series, the index and the columns, you will get actually a data frame. So here you will get a sub data frame with records 5, 6, and 7, and the columns between these 2 columns. And that's what we get here. Okay. And yeah, you can use the syntax to modify specific values like we've seen. So you can take record 5 and change its subunits to whatever value you want. And then when you access this record, you will see that it has indeed changed, and you can then restore it. Now let's see how we can add more columns. So adding more columns is actually very straightforward. It's like adding records. It's like this dictionary syntax that we've seen. You just assign an unexisting label, and you will get a new column. So taking the original data frame and assigning a non-existing column and then giving it some series with the matching index to the index of the original data frame, we'll just create this new column. Now, if we begin with existing column and just modify them or use some vectorized operations on them, we are guaranteed to get a series which has a matching index. So it's actually a very efficient way to create columns. So using just this one line of code, we add a new column to the data frame whose values is just the average between the inner and the outer radius, like you see here. Okay, and you can see that we have this new column.
Doesn't have to broadcast this to each one of the rows.
Yeah, so that's what is called a vectorized operation. So remember that this column is a series, which is the exact length of the data frame. And so does this column. So both of them are series with corresponding indices. So when you use the plus operation on them, you will get a vectorized addition between them. And again, it will retain the original index. And when you divide it by 2, it will know to broadcast it and to do that element-wise. OK, let's see a more sophisticated example. So let's say we want to filter out outliers. Okay, so let's say we want to add a new column, which is called isOutlier, which for each record will give us a true or a false, whether it's an outlier or not. And we define an outlier as such record that either of its inner radius or its outer radius or its average radius are outliers, where for each of those we define an outlier as something that is more than 2.5 standard deviations away from the mean. So let's see how we can do it very efficiently using these vectorized operations. So we first define a function which we call check outliers, which get a series and the number of standard deviations that we want to check. And what it does to the series, it takes the values of the series and subtracts the mean of the series. So again, this is just a number, this is a series. So subtracting will do this broadcasting, which will reduce this number from each one of the values within the series. And we want the absolute values. Again, this works in a vectorized manner. And then we want to see whether it's more than the number of standard deviations that we got, numbers the standard deviation of this series. And again, this is a number, this is a number. So the multiplication is just a plain old Python number. And when we compare a series to a number, it will, again, broadcast that and do that element-wise. So it will check whether each of the records, the absolute value difference between those values and the mean is more than this number, which will essentially check for each record whether it's more than 2.5 standard deviations away from the mean. Okay, so we end up getting a Boolean series with the same index of the original series. And then we apply it on the inner radius column and the outer radius column and the average radius column. And for each of them, we will get a corresponding Boolean series with the same index. And so we can use the OR operation on them, which is a vectorized way of doing the element-wise OR between the values. So for each value, we get whether its inner radius is an outlier according to this function, or its outer radius, or its average radius. And then we just assign it to a new column, and we're done. Questions? OK, now if we want to remove a column, we can just use the del statement, like you see here. And we no longer have this column. Another way to remove columns is to use the drop function. Now this is different than the del function. The del function actually changes the original data frame. The drop function will not change the original data frame. It will instead return a new data frame with these two columns being dropped. Okay, so it's like when you do something like querying specific columns. Say you just want, say, the family and the genus. So this doesn't actually affect the original data frame. Okay, it just gives you a new data frame, which is a view into the original data frame. Now, of course, if you change this data frame, it will affect the original data frame because it's by view reference. And similarly, if you change what you get from the drop data frame, it will change the original data frame, even though it's not the same data frame. Okay, so it doesn't really change the original data frame. It just gives you a view of some subset of the columns, where if you use the drop function, the subset will be everything except of the columns that you specify. And notice that we need to give the axis columns attribute. Otherwise, by default, the drop function thinks that you want to drop actually specific rows. So by default, it will expect some list of row indices, and will give you a sub-data frame without those rows. OK, so we spoke about how to add and remove rows. Now, if we want, columns. Now, if we want to add a row, again, we do it using this dictionary-like syntax. So we just assign a non-existing record. So that's one way to add a new row. We just we use the lock attribute and then give some non-existing index. If we use the length of the data frame, it will make sure that the new index is just the next appropriate index, assuming that we have the 0 to n-1 kind of index. And then it can be anything that is compatible with adding a new row. So you can give it a series with indices matching the column names and the values of these columns, or you can just give it a dictionary and it will convert it automatically to a series and add this new record. So if you give it a dictionary, it expects the keys to be the column names and the values you want to give it. And you can see that now, when we look at the tail of the data frame, we see that the last record is indeed this new silly record that we created. Yeah?
We use the keys like the column names. The order is not important, right? We can change orders.
Yeah, you can change order later on. But I mean, when you assign a non-existing, when you add a new row by assigning a non-existing index, then the behavior of Pandas will be to add it to the end of the data frame.
And a new column?
Sorry?
It will add out to the
A new row we added here, okay? There is also a syntax to add something to the middle of the data frame if you want. Okay, now if we want to remove rows, there are many ways we can do it. One way is just to maybe use the iloc or some other slicing to just slice away the rows that we don't want. So for example, if we take only the first 419 rows, it will actually not include the 420th row that we just added. So this will give us a new data frame. And by assigning it to the original variable, we will get that now the data frame is without this new row that we added. Another way, like with columns, is to use the drop function, which by default refers to row indices. So for example, if we want to remove row 416 and 418, we can just give them, and you can see that the data frame that we get doesn't include those rows. And again, notice that it doesn't really change the original data frame. By default, we're going to see that there is a way to ask drop to change the original data frame, but by default, it will just return you a new copy of a new data frame without those rows. Questions? Okay, let's take a closer look at those index objects which we referred to. So if we go to the index attribute of a data frame, you can see that we actually get something that is an index object. In this case, it's an integer index. And we can also print it. So if we print it, we actually get the indices of all the rows in the data frame. And the index, like the values, also has a data type. So in this case, the data type is an integer. And we can also ask for its length if we want. Now remember that each of the columns will give us a series with the same index, which is the index of the original data frame. So if we take the index of some columns, we actually get the same index no matter what column we ask, which is the exact same index of the data frame itself. But on the other hand, if we ask for a specific row, then we get a series where now the index is the column names. So now if we take the index of a specific record within a data frame, you can see that the index is just the column names, and its D type is just object because it's strings, and the length is 14, which is the number of columns. Okay, so that's sometimes counterintuitive to people because people are used to think about the actual index of the data frame to be the index, but the columns are also indices. They just happens to be an index of strings, which are the column names. Now we can change the index of the data frame and we can set it to be some other column. For example, we can take the data frame and use the setIndex function using the entry ID column. And that this will return to us a new data frame, which is like the original data frame, but with the index now being the entry ID and the original index being discarded. So you can now see that the entry ID, which is strings, becomes the new index of this data frame. Okay, and I think this actually answers your question from the beginning. So you asked whether we can give some other column to a data frame. So yeah, we can do it. So we can just use df entry ID, and then you asked, for example, if we can have the subunits indexed by entry ID, and that's the way we do it. We first set the index to the new index that we want, and then we query a specific column. And now we will get the column values indexed by this other column, which becomes the index. Now, when you set a column to an index, you better make sure that this column actually has unique values. If it doesn't have unique values, you will get some undesirable consequences. So it's important to keep the index unique. Okay, so make sure that, for example, you won't use, I don't know, the family as an index. It's not a good index because the family is not unique. You have many records with the same family. Questions?
Can I drop the index column?
To drop?
What happens when I drop the index column? Like
You can reset the index. I mean, so every data frame must have some index. If you reset the index, the index will just be the default 0 to n-1. So we can take this entry indexed data frame and use the reset index function and actually drop it. And now again, we get like the original index of 0 to whatever. And we no longer have also the entry ID because it first became the index and then we dropped this index. So now we don't have it anymore. Okay? Okay, and notice that now that we have a data frame which is indexed by names, when we use the log attribute, we now need to specify indices by name, not by integer. So we can take, for example, the record that has this entry ID, and we get the appropriate record.
you have to assign the new index to a new data set, or can you do it on the original?
Yeah, you can. I will show you later how you can, all the operations pretty much. So by default, all of Pandas operations will not work what is called in place. So they will not affect the original data frame. They will just return you a copy of a new data frame with this modification taking place. But pretty much all of the functions can get an in place argument which asks the data frame to actually change things in the original data frame.
Now if you change something with this entry index data frame, it will not change the original one.
No, if I change something here, it will change the original data frame. It's not the same data frame object, but they refer to the same underlying data. That has to do with this view thing which I spoke about at the beginning. If you want to change things to this data frame without affecting the original data frame, just use the copy function to create a new copy of this data frame, and then you can safely modify whatever you want. Okay, so it stems from the fact that Pandas tries to be efficient with memory. It doesn't want to duplicate the data every time you do some operation. So it just gives you the same data, just indexed maybe in a different way or something. But it will not actually copy the data to someplace new. What did I try to show you here? Okay, yeah, and so once we get this column, it's the column of the new index data frame. It's just like any series. Okay, so this time when you get a column, we get that the index is the entry ID and the value is the family here. And when we take the index of this column, it will be like the index of the original data frame, which just the entry ID is. And again, if you want to access a specific value, you can take the family record and ask for, the family column and ask for this record, or you can do it in a reversed way, first asking the record and then asking for a value of the record, or you can even do it directly, asking for a specific record and a specific column together. Yeah, and like before, you can do vectorized operations if you want. So when you do a vectorized operation on columns from the original data frame, or you do it with the new indexed data frame, you essentially get the same results, just with a different index, because here we have two data frames with the same index with a vectorized operation, so it works. Here we have two series with the same index, so again, it works. But if you try to do some vectorized operations with one column taking from the original data frame and the second column taking from the newly indexed data frame, then it will not work, because now they don't have the same indices. Okay, so you see that what we get is all over the place. You get some of the indices, the entry IDs, some are just the original numbers, and you get a mess. Okay, like I mentioned, the columns are nothing but an index. So if you check what the type of df columns, you see that it's just an index. And df.columns will give you an index, like df.index will give you an index. And you also can check the data type of each of the columns. So dataframe.dtypes will give you a series mapping each column name to its data type. Questions? Okay, let's quickly see how we can rename columns and indices. So it's quite easy. We can use the rename function, which again will not change the original data frame. It will just return a copy with a new data frame with this change taking place. So you can use the rename and then specifying you want to change the columns. So you do it with the keyword argument columns. And then you can give it many things. For example, you can give it a dictionary that will map old column names to the new column names that you want. For example, you want to change inner radius to IR, and outer radius to OR, and average radius to AR. So you specify all of that in a dictionary. And you see that what we get is a data frame with the new column names. You can do even something more fancy. You can give a function, and then what Pandas expects to get is it expects to get a function that for each column name will give you, for each existing column name will give you the new column name. Okay, so it will just apply this function on all of the column names. So for example, we can have a function that changes spaces into underscore and changes everything to lowercase. And you can see that this function was applied on the column names, and now we got new column names. And the exact same thing works for the index. So we can use rename, and then for index, give a dictionary. And now you see that it mapped entry, so record 418 turned into -1, and 417 turned into -2. Okay, let's see how we can create data frames and series objects from scratch. So up until now, we worked with a data frame that we loaded from a file, but we can also create it ourselves if we want. So we can call the constructor of series. So just pd series. And then if we just give it the list or anything that is list-like, so any iterable objects, it will just create you a new series with these values. And by default, the index will be the default index. So you can see that you get a series with those values and a default index. If you want a more specific index, then no problems. You just specify it using the index argument, and you can give whatever indices you want. So here we have the same series, but with different index names. And you can also give it a dictionary, and then it will use the keys of the dictionaries as the index, and the values of the dictionary as values, and it will convert this dictionary into a series like you see here. Now to create a data frame, again, you can do it in multiple ways. So one way, again, is just to create it, to give a dictionary. But this time, when you try to turn the dictionary into a data frame, what it expects to see, it expects to see that the keys of the dictionary will be the column names, okay, so not the index, the columns. And the values, it expects to get some iterable object that contains the values for these column. And it has to be the same length for all of the columns. So you can specify a value column which has these values, and an is big column that has these values, and you get the appropriate data frame. And if you want to enforce a specific column order, you can also specify a columns argument. And then notice that even though in the dictionary we first specified is big and only value, when we specify the columns are value and is big, it actually takes this ordering if you want some specific ordering for your data frame. Another way to create a data frame is to give a list of lists or a list of tuples or any iterable of iterables. And now this time, it will not specify the data frame column-wise, it will do it row-wise. Okay, so when you do that, each entry in the original list is a different row. So you get the first row values, the second row values, the third, and so on. And then again, you can specify column names if you want, and then just the first one will be the value, and the second one will be is big. And on top of that, you can also specify a different index if you want by using the index attribute. And then you see that you also get a different index for the data frame. So another way to get, so here we essentially give it some two-dimensional structure. So instead of list of lists, we can just give it a two-dimensional array, and then we can convert it to a data frame. So for example, we can use NumPy to create a random two-dimensional array, so a matrix with 5 rows and 3 columns. And then we can just turn it into a data frame, and we get a data frame with 5 rows and 3 columns. And we can also specify the column names, and you see that we get A, B, and C. Now, if we want to get back the underlying values of the data frame, we can just use the values attribute, which will give us a NumPy array of 2 dimensions in the case of a data frame. So this will give us the 5 by 3 NumPy array. Okay. Now, let's see how we can iterate over records in a data frame or in a series. So there are many different ways to iterate over records in a data frame. One way is just to use plain old indices using, say, the range. So we can take the length of the data frame and then the range of that to get all the indices. So here it's the positional indices of the data frame, and then just use the iloc attribute to get the record by position. And then from that record, we can take whatever values we want. And here, for example, we calculate the sum of the charge. So we add it each time, beginning with 0. And you can see that by the end of this loop, we get the charge sum, which, as we expect, is just equivalent to querying this column and using the sum function. Another way to do that, an even better way, is to use the iterRows function, which will just let you iterate over index and record. Okay, so each time, on each iteration, you will get the index of the record and the record itself. And then you can just access whatever you want within this record, and again, do the same calculation and get the same result. Now, I said that the second option is better. Also, it's more elegant. You can see that it's less code, but also it's more efficient. So let's try to compare the performance of these two approaches. So in option 1, we use positional indices. In the second option, we use the iterRows function, which gives us some iterator over the data frame. And let's use the timeItMagic command to compare the performance. So you can see already that the second option is over 2 times more efficient than the first one. So it's more efficient by far to use the iter rows instead of querying by position each time again from scratch. And what is far more efficient is just to use the sum function. Okay, so this doesn't involve any Python code. This does everything in native code in the efficient implementation of Pandas. And you can see that it's 62 microseconds, not milliseconds. So it's like 1,000 times more efficient than this option. Okay, so it's quite a staggering factor to see something that is 1,000 times more efficient, and also much simpler. So this is that much code compared to that much code. Okay, so just use the native or the built-in blocks that you get from Pandas. It will be more efficient in your programming time and in performance time and everything. Now, if we want to iterate over a series, again, we have some different options. So one way to iterate over a series is just to treat it as an iterable object. So we can just use a for loop and for each value within the series. And this will just work as we expect. Okay, so when we do that, what we iterate over is the values, not the index of the series. And each time we'll just get the next value within the series. And again, we get the same result. Or we can use the iterItems function, which is very similar to the iterRows function of dataframe. So this will give us the index and a value, each pairing of this series. So this is very much like the items or the iterItems of a dictionary.